our CECs in our environment. Back then, there was a little bit of data coming out of European science, but really in the U.S. we had no clue what was going on, and obviously we wouldn't be here today if it wasn't a big fat yes. We're seeing these things all over the place. And they're stable and mobile enough to get into streams, groundwater, our sources of drinking water, and really it's complex mixtures. Rarely do we find a single compound at a time. They're kind of like cockroaches. You find one, you know dang well there's a whole host of them out there. So, and that's the complicated aspect is once you get into the exposure side, certainly looking at effects to one compound at a time is important. It does provide some understanding, but in reality, whether it's fish, bacteria, humans, you know, it's really that cocktail, and that's kind of the more complicated aspect is there certain combinations that are just going to be bad actors or not? And that's where I think we're starting to learn a lot, but I think that's one of the big areas that are research gaps. We just don't know what the consequences are to these very complex mixtures that are out there. And for us, again, since we're looking at source to receptors, we look at a whole range of source pathways. Getting into sources is a very important aspect, but in reality, it's really tough. I mean, you're out there sampling a hog lagoon. It's not fun collecting a sample, and the chemists tell me it's even worse analyzing that stuff. But it's really important to understand what's in the starting material. What is in that starting material so you can see, are we seeing those same things in the environment? And we're looking at a whole range of sources. It's very complex to collect, it's very complex to analyze, and I'll just get into a couple examples of the kind of things that we do, and really then we integrate that with fate and effects kind of research as well. So one of the things I thought that we all kind of may have some perspective on or interest in is landfills. We did a national landfill leachate study. We did two phases. Actually, the first phase, what we call fresh leachate. What is the stuff that's being generated right out of the leachate? But because we know a lot of that leachate is either, actually, and I didn't realize until I started looking into this, a lot of that leachate is actually collected and then actually piped or trucked back to our wastewater treatment plant. So a lot of times when you talk about some of the disposal recommendations, well, you just mix it with coffee grounds or kitty litter and then throw it in the garbage. That's certainly good in terms of preventing secondary exposure, whether it's dumpster diving or kids thinking they're pretty pills that actually candy. So there's some safety considerations that's good, but in terms of preventing environmental contamination, is throwing it in the garbage really effective or not? Because it may just be a more circuitous route to basically get back to the wastewater treatment plant. So initially we look at fresh leachate, but again, we know that's not necessarily what's getting in the environment, so we paired that with what we called final leachate. And we looked at a whole range of contaminants, looking at 200 and some contaminants emergence concern. This kind of slide, you can look at the fresh versus final results, and both these fortunately are published, and if you have any interest of looking into these, certainly let me know or dig into them, and you can look at the more detailed results. Actually there's similarities and differences when you look at fresh and final leachate. Certainly we find all kinds of stuff in both, whether it's fresh or final. If you looked at the most frequently detected compounds are pretty identical, shifted order just a little bit, but basically it's bisphenol A, cotinine, which is a nicotine degradate, and lidocaine were basically both found in both fresh and final leachate. So almost everywhere did we find these compounds. And we look at a given sample, most of them we find all kinds of compounds. Again, that's just what we're looking for. If we looked at the scope, we'd found even more stuff, but medians of 20 to 30 compounds, again, it's lots of stuff. And more interestingly, not really surprisingly, but interestingly enough, the levels themselves range from nanograms per liter, so like subparts per trillion, up to milligram per liter levels. And that's where some people like to call these compounds, when we start looking at milligram per liter level, that's not micropollutants. Now you're talking about nutrient levels. You can see some of the BPA, particularly in both fresh and final leachate, but final leachate, 17.2 milligram per liter. That is extremely hot. Now, does that have any effects or not? That's another question. Certainly, BPA is known to be weakly estrogenic, and certainly far less estrogenic than an estrone. But when you're in 6 orders of magnitude higher concentrations, it still could have potentially some environmental consequences. So this just kind of documents that, yep, we're finding these things both in fresh and final leachate. And just a little more comparison, we had 10 landfills. We looked at both fresh and final, so exact same landfill, just one was the freshly generated leachate, and the other basically what is leaving the landfill. And certainly you can see that there's similarities and differences. The big thing is, the total, we summed up all the hits basically to come up with the total contaminants emergent concern concentration. Both were high, but certainly much higher concentrations in general as a group than the final leachate. So you do see that treatment, whether it's holding into holding ponds, or there's some treatment going on site, that it does have some effect at generally reducing the concentrations of what's ultimately going out and getting the environment. But still, even with whatever storage and treatment that's going on, there's still lots of stuff that's taking place, or still that's present in that leachate. And now, the question is, when you bring back to a wastewater treatment plant, for example, is that having a big enough of an impact to maybe tweaking up the concentrations in a land or in a wastewater treatment plant, or is it the volume so small that it's just getting diluted and mixed, and you just can't tell the difference when you put that hot leachate into a wastewater treatment plant? And that's kind of the work that we're following up with now. So kind of get into the fate and effects aspect. We have what we call a field laboratory, one of our field laboratories. It's 4 Mile Creek in central Iowa. So really, these are ideal scenarios to conduct hypothesis-driven research, but we're in the field setting because you never can replicate things. You can do some important things in the laboratory, but it's impossible to really replicate the real world in a laboratory setting. 4 Mile Creek is good in terms of it's a small headwater basin. It's small, so it's easier, it's better. It's still complicated, but it's less complicated than looking at a big basin with lots of streams coming in and groundwater mixing and everything else. So we try to keep things on the headwater side. It's certainly as a single source, so it's effluent impacted, so we kind of know there's a strong source. We look at things above and below, clear effects to the system. The plant itself, although we didn't know it at the time, but the plant then underwent a major change, which then gives us a whole new set of hypotheses to look at, and I'll talk about what that change was here in a minute. And the good thing, well, kind of fortuitous after the fact, that again, we didn't pick it because of that control above the wastewater treatment plant, but there is a low head dam a mile or so above the wastewater treatment plant. So we looked at fish populations and other aquatic populations. We can really separate above and below and see, is there impacts to the ecosystem by this wastewater treatment plant. So we sampled the effluent lots of times. This is just one sample that we happen to have published. I threw that up there, but just to show, looking at pharmaceuticals, that it's there's lots of stuff there. 52 pharmaceuticals detected in this one time. Here's the top 6, and I showed this on there because historically we used to look back when we first did the stream recons. We did a 1 liter bottle. Looked at pharmaceuticals and looked at maybe 14 to 20 pharmaceuticals. At the time, that was fantastic. People hadn't been looking at it, so it certainly was a new tool available. And in those early samples, in the early method, carbamazepine was just always found everywhere. That was the compound we thought, it's just, we're finding it everywhere, everybody's finding it everywhere. That's an important compound. And you see in this study, it's down there at 10. So with the new method, now we can look at 110 pharmaceuticals, and rather than a 1 liter sample, now we're at 10 mils. So we reduced the volume. It's so much easier now in the field to collect the sample, but we broadened our scope. And now you can see there's all these other compounds that we knew were out there, or likely were out there. We just didn't have the ability to measure them. And now we can see all these other compounds were actually higher than carbamazepine. The first one is fexofenadine. That's an antihistamine. Metformin, which Rebecca will talk about in the next presentation. That one is, again, that's kind of the new carbamazepine. We're finding that everywhere, much higher concentrations, and as you'll hear in the next talk, there actually could be some more effects stuff as well. But again, just shows as we look at you only can see what you measure, and with time, as we get better tools available, we can look at more compounds. Venlafaxine is a degradant. I think we're still way on the shy side of things with degradates, but shows we just need to look at active ingredients. We need to look at degradation products, but really think, it's a huge universe out there. We just need to figure out what is the highest priority, because we're never going to be able to measure everything, but we need to figure out what is the most important things we need to be looking at. So again, just shows that when we look at the source that's out there, the main point of that slide is source out there. It has lots of stuff in it, and so that's going to have an impact on the water quality of the system. What I'd like to show in USGS, our bread and butter is looking at fate and transport is, when you pick a field laboratory, you need to understand the hydrology. In many cases, I think some of the studies I see out there really kind of skimp or just ignore the hydrology. And you really want to understand the system, you got to know what the hydrology is, or you're going to have some problems with interpreting results. In this case, you can see the hydrograph here on the upper right. The hydrograph is bouncing up and down continually because there's this diurnal pulsing from the wastewater treatment plant that's really driving the hydraulics of the system. So a lot of times, and even myself when I was looking at pesticides, when you look at a stream, you go there during base flow conditions, you just what we call synoptic sampling. When things are stable, you sample one bridge and you go down to the next bridge and collect the sample and really don't take residence time into account. And that's fine when you have more natural systems, but for this kind of artificially impacted system, there is no true stable flow conditions. You're always getting this bouncing around. So if you collect a sample at one bridge, you may be at the peak of the hydrograph, you go kind of randomly go down to the next bridge, you may be in the trough, and you certainly have an idea what's out there, but in terms of trying to understand what happened between point A and point B, or is there any sort of attenuation going on, you really can't make those interpretations without really understanding the residence time it takes for water to flow from point A to B. So you really want to try to follow that same package of water as it moves downstream as best you can. Obviously you got longitudinal dispersion that kind of complicates things, but at least you're trying to take the hydrology into account. So really you need to do that first. You can do some exploratory stuff, but once you get it deep into the faint transport, you need to understand the flow system. And this example, again, another shot of kind of the start of this rhodamine, the dye tracing test that we do to get an understanding of the travel times. In this case, you can see in the slide on the left that we just started putting in the dye. And the slide on the right, we see obviously it's moving downstream, and then if you kind of notice there, all of a sudden you see, what the heck, there's some dye moving upstream. I mean, who would have guessed without knowing the flow system at these kind of, and this is very low flow, so this is kind of not drought, or we catch drought conditions later, but certainly low flow. But you still would have, you just figured gravity, well, I'll just go 50 feet above the outfall and you're good enough. Well, in this case, these low flow conditions, there's this eddy effect that starts taking place. And we never would have captured that. All we proud of, after the fact, we would have saw some concentration like, man, that looks really close to the effluent. But this really proves that when you throw in dye and you start seeing dye going upstream, that you got other things going on, and that really is important to really understand your results when you start collecting samples and getting results back from the laboratory. And this is just some early results when we were looking at antidepressants. Again, trying to get an idea of what's in the system. We were looking at basically fish community structure, and we see, just quickly without having any slides, but basically we see a better diversity upstream of the wastewater treatment plant. Downstream of the wastewater treatment plant, no problem with fish biomass. I mean, we were doing the fish shocking with just floating little barge like a little bathtub, and we were catching so big a carp the barge was starting to sink. But the problem was, I mean, plenty of biomass, but it was really the fish, it's the tolerant fish species. You weren't getting that really good diversity as we were seeing upstream, and it's starting to kind of recover as you get farther away from the wastewater treatment plant. But the pain point here is we did that community structure stuff. We saved white sucker because that's kind of was a fish species that we looked at Boulder Creek, which is another field laboratory that I'm not going to talk about today, but we want to basically have the same species so we can do some more comparing and contrasting. And certainly see the first column, the wastewater treatment plant, you can see the effluent concentrations are very comparable to what we're seeing in Four Mile Creek itself, both at 2.9 kilometers below and 8 kilometers below. We get some attenuation, maybe some dilution going on, but really what you're seeing in the effluent is pretty mirrors kind of what you're seeing in the effluent. But we're seeing in the fish brains, the fish were gracious enough to volunteer their brains for science here, that we definitely see uptake into the fish. Again, at this point, we don't know what's going on, but they're uptaking into the fish. But interesting enough, again, you see that mixture stuff, but what was most prevalent in the water was not what was most prevalent in the fish brains. But this data was useful for colleagues, particularly Heiko Schoenfuss, that we're working with quite a bit. So it gives us a frame of reference. We know what's in there in the real world. He can use the laboratory studies using environmentally relevant concentrations. So he's not just smacking them with, orders of magnitude higher concentrations we'd ever see in the real world. He's looking at environmentally relevant concentrations, both singly and in mixtures. In this case, he's doing the 12-day larval fathead exposure experiments, so they're quicker. You don't need these 30-day exposure experiments looking at adults, so they're quicker, they're easier, and they're smaller. So you can just use beakers rather than these larger aquarium, which takes a little more maintenance and so forth. And basically, we found that antidepressants, it slowed the predator avoidance behaviors for the larval fathead minnows. So basically, that sea start mechanism, they bend to a sea and they escape the predator responses. So the antidepressants themselves didn't kill the larvae, but it slows the reaction to predators. And when you're in the food chain, you really don't want to be slower to reaction to predators. So there can be some consequences for at least being exposed to antidepressants. And again, that's just a single class of compounds. When you mix that with everything else, there could be even more effects. But definitely shows that, at least for this class of compounds, it's not just a scientific question that, oh, it's cool, they're out there, let's follow them along. That they actually have some real world effects, and that could have cascade into higher organisms as well. And that's what future research is looking into that into more detail. Okay, so the other thing that we did for Fromont Creek is what others hadn't been. Others have kind of looked at, well, let's look at the stream, let's see how the concentrations go downstream. But very few people looked at, vertical and horizontal gradients in the hyperic zone, in that shallow groundwater system associated with these effluent impacted systems. So we put a whole range of piezometers in, again, in the stream bed itself and along the banks. Again, just tried to capture the water table. We didn't go very deep. Unfortunately, the materials we could hand auger, so we didn't have to, pull in geoprobes or any sort of drill work. We can all do it by hand. Although tree roots were a pain in the butt to get these down even 10 feet. But the big thing is similar to what we saw in the stream. Basically, if you remember that pattern of the stream hydrograph bouncing up and down diagonally, seeing the same thing both under the stream itself and in the banks close to him. I think we went within 20 meters or so. But really, it shows that it's just driving the whole hydrologic system, both in the surface water and in the shallow groundwater. Again, when you look at then these piezometer results, again, you see that effluent source. Not surprising, obviously, we knew it was in the effluent, and you can see that there's not much above, although, again, when you get higher above that eddy recirculation, you see not much up there, and then you see the effluent really having a strong impact on the stream water quality. But in this case, you can see that in October of 2012 was very, very low flow conditions, prolonged lack of rain, and you can see that eddy really formed and had a very high extent in terms of even going around the bend, which was much higher than I ever would have suspected. And every time you get a rain, it kind of busts it up, and if you have frequent higher flow conditions, then that eddy kind of gets broken up and it's minimal. But every time you have prolonged drier conditions, that eddy starts coming back into place. But also you can see that there is pushing of the pharmaceuticals into the bank as well, and that's going to be important as we get into this a little bit later on. And then when you look at things, the profile, you can see that first meter in the bank, there's a lot of stuff going on. That's a very active point, whether it's absorption or microbial degradation. We haven't determined that specifically yet, but there's a lot of attenuation going on within that first 1 meter in the bank, where we have about 60% attenuation. But there's some compounds, we had between 10 and 20 compounds can push way into the farthest way that we go, which was 20 meters. So we're still seeing things that can really go way into the bank, and that could have some implications. And the compounds here is a whole list. I don't expect to read them all. The ones in bold were kind of the ones I listed before in the top 10. So the top 10 compounds in the stream were also, a lot of them were the same ones that the top 10 we're finding in the shallow groundwater system. And again, this paper was published in 2014. If you are interested, just certainly give me an email or a buzz, and I'll forward to the PDFs of these papers. And I mentioned there was a change in the wastewater treatment plant. In this case, like in Boulder Creek, they actually went for an upgrade from upgrading from trickly filter to an activated sludge. In this case, it went from basically, normal operation to actually shutting down entirely. That they decided to pump all their waste. The city of Ankeny decided to pump their waste to the city of Des Moines. So they shut things off entirely. So it really gave us a unique opportunity to first look at above and below, what's that footprint of that wastewater treatment plant, but then we just turn the pipe all the way off, and then we see how things react. So that really provided a unique opportunity to really understand what is the impact of a wastewater treatment, what's the footprint. And initially, I won't get into a lot of detail, but initially you think, well, you see all those pharmaceuticals come out of the wastewater treatment plant, that must be, this is going to have a big improvement on the stream itself. And for chemistry, that's probably true. But one thing that a lot of people don't think about is there are actually some benefits of a wastewater treatment plant. And this is October 2012. This is during the height of the 2012 drought. And you see the picture on the top that we're above the wastewater treatment plant, and the hydrologist there can straddle the whole stream. And we go below the wastewater treatment plant, it looks like a natural system. And most people, as you're driving by, just don't realize, in the drought, you see, well, there's still water there, and just never even thinking that water is basically pure effluent at this point. It was like 99.9% effluent. So really, fish like water. So even in drought conditions, you're having plenty of water. So there's some benefits. The other thing that was interesting enough, in the winter, the effluent actually causes a warming effect. So really, in Iowa, as in Illinois, the streams freeze solid, although this was a weird winter. So Certainly, but there's periods where the stream is just going to be totally frozen, where with that warm effluent coming in, it keeps the stream open, and then as the water gets farther downstream, it cools off and the ice encroaches in the banks and will finally freeze. And in this case, and when you have summer drought conditions, there was huge fish kills in other streams because they were heating up to 90 degrees, and the fish were just, croaking because they just couldn't take the higher temperatures. In this case, in the summer, the effluent is actually causing a cooling effect. So there's some benefits. And actually, just kind of a quick aside, I was deploying some POSIS during the winter above the wastewater treatment plant, and you're in 0 degree water for X amount of time. Your feet are just freezing, and you walk down into the effluent, it's like, it's a sauna. It just felt, it's kind of weird. After you think about it, it's like, this is great. It's like, okay, well, maybe this isn't as, but it's warm my feet, so you kind of tolerate it. It's okay, it's effluent, I'll take it at that point in time when your toes feel like they're going to fall off. So anyway, so that's their aspects. Just want to kind of point out that there can be some benefits, at least in terms of the water presence, but as you see here, well, and then we'll get into the chemistry in a second, but really it shows the one thing that was an immediate response to the hydrologic system. Again, if you look at in the left part of the graph, you see that again, you see that diurnal pattern I've noted several times already. Got a rain event that kind of complicates things, but then there was the plant didn't shut off just instantaneous. They start disconnecting the various pipelines, and the first disconnect, the 36-inch line that was disconnected, you can see basically still after that disconnection, you still see that diurnal pattern, but the amplitude is starting to get dampened. You started to bring that, you're not getting as big as swings on a diurnal period. And then they did shut off the rest of the pipes, and then they had a period of maintenance where they're kind of pumping and purging and cleaning and inputting water. So you can see it went from looking at more flat line, and then you see this pulse because they were doing some maintenance as they were shutting things down. And then after all that was done, you could see then the stream goes back to a natural kind of condition where it's flatter, and then it would respond to rain rather than that continual pumping of water from the wastewater treatment plant. So it really shows in the stream itself instantaneous reaction to the hydrograph, to the hydrologic system. And the same is true for the shallow groundwater. Again, it just mirrors what the wastewater treatment plant was doing. We're seeing that same kind of immediate impact to the shallow groundwater, where that diurnal pattern is basically shut down entirely after the plant goes offline. So just kind of quickly summarize in terms of the pre and post results. So basically the last sampling of the effluent just before the plant shut down, which I think was roughly 10 days before, basically it's like 10 days before and 10 days after. This last sample before the plant shut down, 70 pharmaceuticals were found in the stream below the wastewater treatment plant, compared to right after the plant shut down, we're down to 8. So again, you see that immediate reaction to, you shut off the source, then it doesn't kind of bring it down to 0, but it makes a big improvement in terms of what is in the stream. And actually, so in the next bullet, you can see where typically we'd see much higher concentrations in the stream compared to the shallow groundwater. We see a lot of the same things in the shallow groundwater, but we do see generally lower concentration. So the stream is always much higher than the groundwater. But after the shutdown, you can see the reverse is actually the case, where there's more pharmaceuticals in the groundwater than there was in the surface water. Again, it's that lag time. It's going to take a while for things to kind of cleanse itself and pulse out of there. And for the 21 pharmaceuticals we saw in that groundwater, one of the groundwater transects just prior to wastewater treatment plant closure, for those 21, 8 exhibited pretty rapid attenuation. So it didn't take long for, once you turn off the source, it didn't take long for them to kind of be attenuated and not see them in that groundwater transect. But there were still 13 that really exhibited limited attenuation, even over a 1-year time period. So that really shows that it's going to take a while. So when it's stuck in the sediment, they'll get some desorbing. So that groundwater and probably the bed sediment is going to be a long-term reservoir for pharmaceuticals and emerging and contaminants emerging concern in general. Just because you shut off the source doesn't mean you get probably some improvement, and you probably get a flatter slope as you have kind of sediment and groundwater as being kind of the long-term sources of contributing these compounds to the stream system. Again, this paper hasn't been published yet, but it's been submitted to the journal, and hopefully we'll get word on its acceptance soon. What am I doing for time? Am I all right? Okay. So just from an urban example, I want to give a livestock example. Obviously, we're here in the Midwest. Since we have both crops and livestock, I thought this would be of interest to the group. Certainly livestock, there's obviously lots of manure that's generated on an annual basis across the U.S., and that manure is used as a legitimate source of nutrients to the fields. But it's really been, I feel, a really underinvestigated source, partly because it's not as easy as a wastewater treatment plant. You have a pipe coming out the side of the ground. These point sources, they're complicated, but at least you can see the source. You can look at above and below like we did at 4 Mile Creek. But for livestock, it's a lot different story. Certainly, I think the operations themselves can be a point source, but I think what I think is more of an issue is you take that lagoon or you take that pit or you take that manure and then you spread it all over the landscape and it becomes a non-point source. I think that's probably the primary driver, but non-point source issues are a lot harder to tackle than a point source. You really can't. For example, you headwater stream in this National Livestock Study, a lot of these headwater streams you looked at, you really couldn't get above the manure application because the manure is applied all the way up to the headwaters. So you couldn't really get above and below. But we did, I still thought it was an important study. This is what we consider our phase 1. It's taken us a while to get to this point. This study was done a few years ago, but we're now finally getting the results back in the laboratory, so we're going to digest what we learned, and it'll take us into phase 2 in terms of really want to figure out what is the next important question we want to deal with in terms of livestock. But we sampled 19 basins. 15 were various types of livestock, and really tried to at these small headwater basins, most of them were less than 10 square kilometers, some of them were a little bit bigger, tried to get homogeneous animal types. Obviously, that's very, very difficult. I knew it was going to be hard, but it was even harder than I had imagined because there's so many mixtures. Generally, when there's hogs, you got poultry, you got everything else in there. But we tried to keep things as homogeneous as we can. Sometimes there's a few animals of other types, but we just had to compromise and said, well, that's close enough. It was just dominated, but really that's kind of the best we could. And then we used what we call rural background sites as kind of a frame of reference where we didn't go to pristine wooded areas. We went to areas where still row crops, same kind of land use, but there just wasn't either livestock raised or manure applied in those areas. So that was kind of a frame of reference. Collected samples from a whole range of compartments, and I'll show the compartments more specifically, but it's really, again, what's in the manure. We think that's always important, even though it's difficult to analyze and collect. Really want to know what's in the starting material. Look at discrete water samples in the stream itself in terms of base flow prior to manure application, runoff samples after manure application, and then we complemented that with passive water samples, both SPMD and POSIS. So they're basically time-integrated water samples where we threw these things out there for 30 days. So then we can capture maybe anything that's episodic in the stream. So when a single snapshot water sample, sometimes you maybe just missed it. Maybe it rained the next day and you happen to miss a flush coming off. Or maybe they're so low that an individual bottle of water, you just can't get low enough to measure it. But when you basically throw these devices out there for 30 days, it's basically effectively you're sampling a very, very large water sample, and you can pick up low concentrations of stuff. And then we looked at bed sediment as well, because I think looking at more than just the water itself, it's important to look at multiple hydrologic compartments to really understand not only occurrence, but also understanding exposures as well. Look for a whole range of stuff in terms of hormones, antibiotics, antibiotic resistant genes, but I won't talk a lot of the results, but I'm going to give you a taste of them here in a second. This again is the sampling design. I kind of went over this, but this visually kind of goes over what I mentioned previously. Again, when there was a distinct manure application, now in some cases when we also looked at grazing beef operations where they just have access or they have a pasture, so there wasn't any manure application steady. So in that case, we just went to base flow. But when there was a distinct manure application windows, we tried to get in there low flow applications before manure was applied. Again, we collected sample of the manure itself, whether it was applications of manure or if it was, again, a grazing operation. We went out there and just collected samples of various cattle patties. Again, we deployed the passive samplers, and then we did a runoff sample, whether it was after application or just a runoff sample if there was no distinct application in the bed sediment as well. Just quickly with the hormones, the bottom line is we saw hormones lots, certainly saw more in the runoff than we did in the base flow, so it does show that when you apply things fresh to the system, you do get a flushing when you get a rain and kind of a mechanism for transport to the streams. But it really shows that grab water samples alone, whether it's base flow or runoff, you're underestimating the hormones in the system by not having these kind of passive water samples where they're out there for 30 days. So not only did we find more occurrences of sample a single compound like estrone, but just found other compounds you just didn't pick up at all without using these passive sampling devices. And again, bed sediment as well, it just shows that, again, we found lots of stuff in the bed sediment. So really looking at water alone, you're going to underestimate occurrence and exposures by not looking at the bed sediment. Again, that was for hormones. For the antibiotics, again, we looked at livestock manure and just trying to see what is out there. For the manure itself, antibiotics are very, very frequently detected at really high concentrations. Some cases, again, up in that milligram per liter levels when you looked at the raw manure itself. Pretty much found in every animal type, although beef, for whatever reason, at least maybe it's for the suite of compounds we looked at, only about 60% of the beef and 100% in all the other animal types, which was pretty similar to what we found for antibiotic-resistant genes, where frequently detected, except in that case, there was none of the genes for these. I don't remember how many manure samples, but probably less than 10 were in the beef. With kind of at least that rank order kind of matches between manure, in terms of antibiotics, for example, or for antibiotics and their genes. For the water, for the stream itself, we see a much different pattern where the antibiotics itself we've really found sporadically detected overall in the water samples, only at 16%. However, when you focus on just those basins where there's a distinct manure application period, and we collected runoff after that period, then we found antibiotics in about half the sample. So we definitely see there is a window or a time period where they're going to be more frequently detected. Now, the sediment was a different story. We found antibiotic resins and antibiotics frequently detected in both. So it really shows that, for the water, I jumped ahead a bit. For the water, it found that antibiotic resistant genes were really prevalent, regardless whether it's base flow or runoff. It really shows that there's something else different going on with the antibiotics. So maybe the antibiotic isn't the only driver of what's causing, and probably isn't the only driver that's causing the resistance taking place in the stream water. And again, for the sediment, found frequently in both. So again, much different story in the sediment than we found in the water itself. Am I still doing okay for time? 5 minutes? Okay, good. Well, real quickly, I'll start kicking up the speed here, although I talk fast enough as it is, but try to follow along. So again, we always want to tie everything together. So again, working with Heiko Schoenfuss, looking at larval fathead minnows. Again, not just show those compounds out there, but is there effects or not? In this case, you can see that a number of the samples we looked at, these are high volume samples, about 8 liters of water that we collected for Heiko. And again, we found no effects when we look at the rural background sites, and unfortunately we didn't get every sample at every site. We had some issues that some of the samples were inadvertently compromised in the laboratory, but we did see there was effects to about half the livestock type samples. About half had some sort of effect, whether it was reduced survival, reduced growth, or reduced escape performance. But when you look at the runoff samples, we found about 80% of the runoff samples had some sort of effect. So again, it shows there's effects out there, and we just now need to follow up to really understand other types of effects. But it really shows there could be consequences of these compounds that we're showing that are in the system. So kind of at the last thing I want to talk about today, just looking at national park research. We're trying to have a growing set of national parks we're trying to cover, looking at emerging contaminants, just because they're quote unquote our pristine settings. There are a lot of natural wildlife, sensitive wildlife is in these populations, but they're also a lot of times visited by millions of visitors to a park every year. So again, what we perceive as pristine may not be so much, because we all are going to these parks, and a lot of times we leave our chemical use behind. This just kind of shows quickly some of the stuff we've got on right now, but we have more proposals submitted, more proposals accepted, so hopefully at some point we'll have a really nice network of national parks across the country. We really do a compare and contrasting on a national scale. Just one of the earlier ones we did was Rocky Mountain National Park. Just some examples of 4 of the types of sites we're looking at. Again, just visually looking at them, it's like, boy, they're nice and pretty, they're pristine. Not going to anticipate we see much. But when you look at, again, this is just with the water itself, you can see a whole range of things that we found. Those that are highlighted in red, are those that are endocrine active type compounds. And you see things like caffeine. We found caffeine in every one of these sites, and some hotter than others. So even we find them in what we call the kind of backcountry sites. We really have to hike in to get to them. So they're not adjacent to a road. But you hike in, you're still people out there, and when there's people out there, everybody kind of leaves their little deposit, or maybe even just putting sunscreen. When you're high elevations, you need to put sunscreen to prevent sunburn. So you you put stuff on your body and you go into the water, you can actually cause contamination, or you throw a cigarette butt into the water, you can leave things behind. So basically the point is, even in pristine settings, we're finding these things, and now we're following up to determine, is there effects to these compounds to trout or other type of wildlife. And with that, I'll end with a shameless plug, helping organize a conference. Some of you may have been to the last MCON conference that was in Iowa City in 2014. The next conference is going to be in Sydney in 2016. I know that's a long ways away, but if you happen to be in the neighborhood, I think it's going to be a fantastic conference. So hopefully there's a time for a question or two. Thank you.
Are there any questions? Take one or two questions.
It's all self-explanatory.
Just real quick, why did you see an increase in BPA in the final leachate compared to the finished leachate in your landfill stuff?
I think part of that, could have been the big one. The overall study looked at, that was looking at all landfills, so that wasn't a complete. If you looked at the paired where it was actually the same landfills where we looked at fresh and final, I think we saw kind of that diminished. But I think it was just, it's a different, your end was different, so you happen to capture different landfills. But the main point is both of them had milligram per liter levels. So that is super high concentrations. When you look at groundwater or any time environmental contamination, I mean, milligram per liter, that's kind of a typical nutrient levels, not these organic contaminants we rarely see, except these hot type sources see that high concentration. Or pharmaceutical manufacturing facilities, that's another thing I didn't have a chance to talk about today, but that's another source where, typically a rule of thumb, you shouldn't see a treated effluent should not have concentrations rarely above 1 and certainly not above 10 micrograms per liter. We're seeing thousands of micrograms per liter pharmaceuticals in a wastewater treatment plant where there's a pharmaceutical manufacturing facility discharging to it. So you can have locally, you can have some really higher concentrations than you typically expect. So, yep, one more.
I was interested in the results you gave on antibiotic-resistant genes from the manure applications. You selected six mutant genes. That's going to be a very small fraction of all the possible ways bacteria
Absolutely.
are able to generate antibiotic resistance. What was the criterion for selecting these six?
Yeah, that would talk to the microbiologist. I think it was just kind of the earlier, easier ones, and we're just expanding our capabilities. Obviously, methods development is always an aspect. So is I think the tetracycline. So it's basically that just picks the low-hanging fruit. It's not going to cover everything, but that's a starting point to kind of open the lid, so to speak. But realizing there's a whole host of other things we need to look at. But that was our starting point. Yeah, thank you.